Hi, hello friends. Welcome to T Academy. Let's continue the previous question papers of diploma examination. Now, the question here it is. In my previous video, we started from question number 100 to 20. Now, in this video, we will continue from that 121 here. Okay, the question here it is a 220 bar 400 volts, 50 hertz 5 kVA single phase transformer operating at 220 volts 40 hertz supply. Okay, here the condition is a 200 volts input 440 volts output voltage of a transformer having a 5 kVA rating is operating at 220 volts. Okay, fine, same voltage, but what about the frequency? Frequency is reduced here. So can you tell me what is the condition here? Here V by F ratio is a constant. Is it yes? No. Why? Because V by F ratio is 220 divided by 50 is not equal to 220 by 40. Okay. So that V by F ratio is not a constant here. So when the V by F ratio is not a constant, what about the eddy current losses? Eddy current losses is proportional to voltage square. That means they are independent of frequency. And hysteresis losses. So hysteresis losses is proportional to 1 by f to the power of 0.6. Okay, as the frequency decreases, hysteresis losses will increase. So from this we can say that eddy current losses is remain as a constant and hysteresis losses is going to be increases. So see the options here. In all the options are wrong here. That means the correct option will be eddy current losses is going to be constant, hysteresis loss is going to be increase here. Okay, so for this answer is wrong. Next one, observe the question here. The reactance offered by a capacitor to AC frequency 50 hertz is 100 ohms. If the frequency is 100 hertz, okay, then the reactance will be, okay, first case XC1 is proportional to 1 by F1 and XC2 is proportional to 1 by F2. This is a basic formula here. Okay, what is the given? What they are given here is XC1 value is as 10 ohms and here F1 value will be what? It is 50 hertz. Okay, and similarly F2 value given, they given as 100 hertz. Okay, so if you take the relationship here, XC2 by XC1 is equal to, okay, so it is F1 by F2. So from this XC2 is equal to XC1 into F1 by F2 here. So you know all the values here. XC1 is at 10 and F1 is a 50, F2 will be what? 100. Okay, so now you can tell me the answer here. So 500 by 100 is how much? It's nothing but 5 ohms. So 5 ohms will be the right answer for this question here. Okay, we will move to the next question here. So this question is from the transformers here. A 5 kVA 200 bar 400 volts 50 hertz single phase transformer gave the following test results here. So when they perform the test, what are the tests here? First one is the open circuit test, second will be short circuit test. In the open circuit test 200 volts 0.7 amperes 60 watts. Okay, so this is nothing but iron losses. Short circuit test 22 volts 16 amperes 120 watts on high voltage source. So what about this? This is nothing but copper losses. Okay, so in the given question, first you check what is the rated current in the secondary side. So rated current IR is equal to, so how much kVA? So it is 5 kVA. So 5 into 10 power 3 kVA divided by how much voltage are applying on secondary side is 400. Okay, so how much it is? It is going to be 12.5 amperes of current, but they given as 16 amperes here. So for that we need to convert. So copper losses at full load divided by copper losses at short circuit current, so which is equal to, so IFL divided by ISC whole square. Okay, so from this full load copper losses are equal at 12.5 amperes, but the short circuit current they given as 16, so whole square, which is equal to 0.61. Okay, now so WCFL is equal to WCSC into 0.61. So how much they given WSC value? 120 watts into 0.61. Okay, so this losses will be what? 73.24 watts, 73.24 watts here. Okay, now what we need to find? Determine the load for maximum efficiency. So I will write the formula here. So kVA, determine the load kVA at maximum efficiency is equal to, so full load kVA into square root of iron losses by copper losses, okay, which is equal to, so 5 into 10 power 3 into square root of iron losses will be what? 60 divided by 73.24. So if you solve this, you are getting it as a 4.525 kVA. So answer will be A here. Okay, so answer is A. Next one, the HP terminals of a 3-phase bank of 3 single-phase transformers are connected to a 3-phase wire, 11 kV line-to-line voltage. The LV terminals are connected to 3-phase, 3-wire load rated of 1000 kVA and 2200 volts line-to-line. Find the kVA rating of LV winding of each transformer for star to delta conversions here. Okay, so in the given question, there is a transformer bank of 3-phase where input to the transformer is having a star connection and the output of the transformer is having a delta connection. Okay, so they are using 3 single phase transformers here and output like this here. Okay, the total rating of the transformer is 100 kVA. Now what will be the rating of the each transformer? Okay, so each transformer rating we need to calculate here. So see here, whether you take primary side or secondary side, transformer rating will not going to be changed, it is going to be same here. The phase voltage, phase current, line voltage, line currents may changes depends upon the type of connection you are using, is a star or delta, but transformer rating will remain same. So each bank will have 3 transformers. Okay, what is the total rating? 1000 kVA divided by 3. Okay, so 333.3 kVA rating of the each single transformer. So answer will be here, it is 333.3 kVA rating here. Okay, so I will move to the next question here. So it's a theory question here. The short circuit test on a transformer gives it is, so what is it is going to be give? Okay, the equivalent resistance and core losses, okay, magnetizing impedance, equivalent resistance and reactance, magnetizing current and core losses. So see here, core losses is found from the open circuit test. We can call this a no load test also. So no load test, from the no load test we can calculate these losses here. Now see here, here you can see the diagram here. Here we are applying the variac, there is auto transformer, we are supplying the short circuit voltage, ISC current, short circuit current, and WSC wattmeter reading here. So from this wattmeter reading and current and voltage reading, we can find the resistance and the reactance component of this equivalent circuit here. So answer will be equivalent resistance and reactance here. Okay, when you have done the short circuit test on transformer in the laboratory, you are going to calculate this with the help of short circuit current and short circuit voltage and short circuit wattmeter reading. Okay, next one, a series RLC circuit have unity power factor if operated at a frequency. If you take a series RLC circuit or XL XC here. Okay, so when you are operating at a voltage V of sinusoidal supply, then unity power factor means, so UPF, unity power factor means the load will be in resistive in nature. So when the load is a resistive nature, the XL minus XC component should be equal to 0. Okay, XL minus XC component should be equal to 0. So we know XL, what is omega into L minus 1 by omega into C is equal to 0. Now when you solve this, you are getting V is equal to omega equal to 1 by omega square is equal to 1 by LC. From this, omega is equal to 1 by square root of LC. But in the given question, they asked frequency. Okay, they asked frequency. So here they are not mentioned whether frequency is radians per second or the frequency in hertz. So check the answer here. In all the terms, omega is there. Okay, So they asked here angular, if they asked angular frequency, then will be 1 by square root of LC will be the correct answer, but they didn't ask here. So there is a point here. So omega is nothing but 2 pi f is equal to 1 by square root of LC. So from this f is equal to 1 by 2 pi into square root of LC. So answer will be 1 by 2 pi into square root of LC is a frequency here. So at this particular frequency, the circuit behave as a pure resistive circuit here. Next question here. A coil draws 0.5 amperes from the 120 volt 60 Hz source at a 0.8 lagging power factor. What are the coil resistance and inductive reactance here? So coil resistance and inductive reactance we need to calculate here. Okay. So first, by using the formula we can calculate here, simple formulas we can use here and calculate the value of these two here. So what are the formulas here? The first formula is our resistance is nothing but total impedance into cos theta, and reactance x is equal to z into sin theta here. So you should remember these points here. What is z value? Z is nothing but total voltage 120 divided by 0.5 and the power factor is 0.8 here as given. When we convert this power factor theta value here into sin terms of values, then so z value I'll write as it is 120 by 0.5 into sin theta will be equal to 0.6. Okay, you have to remember this simple values here. Okay, once you solve this, that is 120 by 0.5 means it's nothing but 240 into 0.8. Here also 240 into 0.6 here. Okay, simply you can write 24 into 8 and here 24 into 6. Okay, now you can guess the answer here. 24 into 8 will be what? 192 ohms, and this will be 144. So 192 ohms here and this will be 144 ohms here. So this is the answer. Next one, an impedance of Z is equal to 2 plus J80 ohms powered by a source having a angular frequency. So just now we have seen they asked angular frequency here, omega equal to 200 radians per second. What the element should be connected in parallel to Z so that the current drawn from the source is in phase with the voltage. So same concept here, XL minus XC should be value equal to 0 here. So based on this concept here, so what will be the, we know XL value here. What is the XL value? Plus J80. Okay, so plus J80 is equal to XC. That means we need to connect a negative value of this J80 here. Okay, so negative value of J80 means it is nothing but simply capacitive element here. Okay, so the magnitude will be J80 here, but XL minus XC should be equal to 0. So what is the magnitude of SC? It should be minus here. So as they say, simply capacitance value. Next one, how much power is absorbed by a circuit that has input admittance of plus 3 plus J0.4 S carrying a current of 30 amperes. So first Y value they given, Y is nothing but 0.3 plus admittance value they given 0.4, units are Siemens. Now what is the value of Z here? So Z is nothing but 1 by Y, which is nothing but, I can simply fractionalize here 0.3 minus 0.4 divided by 0.3 minus 0.4 here into 0.3 plus J 0.4 here. Okay, so if you simplify this equation here, so 0.3 minus J 0.4 divided by 0.5 will get it. Okay, so from this is a real part and this will be the real part and this will be imaginary part. So what is the real part here? From this R is equal to 0.3 divided by 0.5 is nothing but 3 by 5 ohms here. Now we know that the power absorbed only by the resistive element. So inductive element and capacitive element ideally they won't absorb power. Okay, so P is equal to I square into R here. What is the I value? I value is nothing but they given at 30 amperes, right? So 30 into 30 as I am splitting into square here, okay, into resistance value is 3 by 5. So if you solve this, you will get the answer as a 540 watts. So answer will be 540 watts here. So that is the right answer. Okay. So next move to the 30th question here. The transformer will operate at maximum efficiency when? The standard question, guys. So transformer will operate maximum efficiency when the variable losses of a transformer is made equal to constant losses. So constant losses here. So what are the variable losses? That is nothing but copper losses. Copper losses is equal to constant losses means core losses. We can also call as iron losses. So the answer is copper losses are made equal to iron losses. Okay. Next question here, 131. Transformers are rated in kVA instead of kilowatts because. So the practical reason here it is, when you are going to buy a transformer, the manufacturer, suppose I am the manufacturer, you are the buyer. If you are asking me, I want a transformer, okay, then I don't know what type of load you are going to connect here. Suppose if you are using for induction machines or for resistive loads, I don't know. So when you are asking a transformer, what you will ask? I want a transformer. Then I will say how much kVA you want, that's it. I don't ask that what you are going to connect to the load. Okay. So that's the reason why practical reason is the transformer measured in kilowatts. Okay. So it is based on only resistive load. Okay. But when you are theoretically speaking, there are two losses, iron losses and copper losses. Iron losses is depends upon voltage, copper loss depends upon current. The product of V into is nothing but watts. So depends upon that, we can say that the transformer is designed to have designed is based on the losses here. So total losses depends upon volt amperes. So answer will be the load amperes. Okay, this is the first important. If there is the option is missing, the load power factor is unknown. So this will be the second option here. Okay. Next one, the synchronous reactance of an alternator is due to. So synchronous reactance XS is equal to the leakage reactance plus armature reactance here. So XL plus XA. So XL plus XA is equal to the synchronous reactance here. So the answer will be leakage reactance as well as armature reaction reactance here. Answer is A here. Next one. Yeah, it's a little bit mathematical question, but understand the concept of the induction machines in this here. Okay. If you understand this question, the induction machine concept will be clear for you, right? The power input to a 415 6 poles 3-phase induction motor running at 975 rpm is a 40 kilowatts. The stator losses are 1 kilowatt and fraction and windage losses are 2 kilowatts. The efficiency of the motor you are going to calculate here. Okay. So first of all, the input is given as how much? 40. So 40 kilowatts is given as the input. After that, okay, so how much losses are gone? The stator core losses are 1 kilowatt. So 40 minus 1 will be equal to 39 here. So 39 kilowatts we got it here. Now rotor copper losses. The formula for the rotor copper losses is S into Pg. What is the value of S here? So S value we can calculate. So approximate value of Ns will be 1000, let us assume. Then S will be what? Ns minus Nr by Ns. Okay. So this will be Ns value is 1000, Nr value is 975. So 25 divided by 1000. Okay. So 25 divided by 1000. Like that we can calculate, or we can simply write it as a 0.025. Now this will be 0.025 into what is the value of Pg? Is nothing but 39 kilowatts. Then this will be equal to 975 watts here. Okay. So out of 39 kilowatts, this much of losses are gone. Then what about the remaining here? Okay, the remaining will be, if you subtract this 13 kilowatts out of this, then you will get it as a 380.25 watts here. Understand? Here I am kilowatts, here is in watts. So I am subtracting this, converting this kilowatts into watts and subtracting here, you will get this value. Okay, 39,000 will be, this will equivalent here. I am subtracting this value, you will get the answer this one. Now from that, the friction and windage losses will be how much? It is a 2 kilowatts. So that means 2000 will be here. Whatever the power output, So out of 38025, 2000 less means 36025 watts will be the power output. Now you know that input is there, output is there. So this is the input and this will be the output. What is the formula for efficiency? Okay, efficiency is equal to output by input power. So output power is how much? 36025 divided by input power is 40,000 here. Okay, you will get approximately as 90%. So answer will be what? It is 90% for this question here. Okay, next one. Synchronous machines, which of the following statement is false? Okay, which of statement is false here? Silent pole machine, the direct axis reactance is greater than the quadrature axis reactance. So this is the right statement. XT is greater than the XQ here. Okay, the statement is correct. Next one, the damper bars helps the synchronous motor to self start. Why? Because damper bars come into picture when the rotor speed is changing here. Okay, so when it is a NR is equal to NS, there won't be no damping bar action. Whenever the speed is less, the damper bar come into picture and it is going to be make a self starting here. Okay, that is also correct statement. And next one, short circuit ratio is a ratio of the field current required. So required field current required to produce the rated voltage on the open circuit to the rated open, so armature current on the short circuit. So actually this is a wrong statement. Here if there is a field current instead of armature, this is a field, means this statement is correct, but here the armature is given, so this is the option, correct option here. Okay, so next one, the V curves of the synchronous motors required represents the variation in the armature current with respect to field excitation at a given output power. So this is also correct statement. So the wrong answer, false statement is, this is a false statement. So what is the correct statement here? Here instead of armature, if it is a field, means this one also is correct, but the given armature means is a wrong statement here. So this is a wrong statement that we need to identify in the question. Next one, in a single phase induction motor driving a fan load, the reason for having a high resistance rotor is to achieve. So when the resistor is there, okay, the starting torque is proportional to resistance here. Okay, when the resistance is more, starting torque is more, so that the ceiling fan will give quick acceleration. Okay, so answer is quick acceleration here. Next one, a three-phase synchronous motor connected to an infinite bus bar with a constant excitation is driving a certain load. Okay, operating at a leading power factor. If the shaft load is reduced, so automatically what will happen? Okay, so shaft load is proportional to load angle. Okay, so that the load angle will decrease. Okay, if it is reduced, it means load angle also gets decreases here. Okay, next one, a single phase 2000 volts alternator has an armature resistance and reactance of 0.8 ohms and 4.94 ohms respectively. The voltage regulation of the alternator for a load of 100 amperes at 0.8 leading power factor is. So I will use the formula here. Voltage regulation is equal to, so I into R divided by V into cos phi. If it is leading power factor means I will use minus sign here. If it is lagging means I will use plus sign here. So leading means minus sign I have taken. So I into reactance X divided by V into sin phi. Okay, so substitute the values of here. So I will be what, 100 amperes, R will be what, 0.8 divided by voltage V, it is nothing but 2000 into power factor is 0.8 minus 100 into reactance value is 4.94 divided by voltage is 2000 into sin phi is nothing but 0.6 here. So once we simplify, okay, so the answer will be minus 11.62%, or simply by looking the option itself we can say negative. Why? Because negative value of voltage regulation occurs at leading power factors only. So without doing the calculations, simply you can guess the answer. Suppose if there are two minus values means then you have to do calculations, but in this type of questions you have to use some logic, that's it. Okay, simply if you are thinking logically means you will get the answer. Next one, a three-phase induction motor runs at 1485 rpm at no load and 1350 rpm at full load when supplied from 50 Hz three-phase line. What is the speed at no load of the rotor field with respect to rotor conductors? They given the speed as a rotor conductor's speed. What is the given? That is nothing but NR, which is equal to 1485. Then what is the field? NRS, field resistance, or NRF is equal to NS is equal to 120 F by P here. So in the given question they didn't mention about the poles. Then what is the approximate nearest value here? It is going to be 1500. Okay. Then what is the difference between the question here? It is difference. What is the speed of the rotor field with respect to the rotor field means? So speed here N is equal to, so NS minus NR. So 1500 minus 1485 is going to be 15 RPM. So that will be the answer here. Okay. Next one. Assume the stator impedance of an induction motor is negligible. The frequency of voltage applied to the motor is increased by keeping V by F constant. The maximum torque will be. So what will be the maximum torque here? The given question here. Okay, right. So here the torque, maximum torque is proportional to V by F here. That means when the V by F is a constant value, okay, what about the maximum torque? So T max also be constant. Okay. Now slip value. So slip is proportional to R by X here. So R by X. So slip at maximum. Then proportional to 1 by F we can say. Reactance is nothing but 2 pi F, right? So maximum slip is proportional to 1 by F. Okay. If the frequency of the motor is increased, it means the slip value will be low. That means the maximum torque will be constant, but the maximum torque will occur at very low value of slip here. So answer will be remain constant, but will occur at smaller value of the slip is the correct answer. So next one, induction machines. A 3-phase induction motor is operating at a slip S. If the frequency of the leads, frequency of the supply leads are interchanged, then the slip at this instant will be. So when the supply frequency, supply leads are changed means they are interchanging the phases here, then forward slip becomes backward slip. The rotation will change here. At the time slip will be equal to 2 minus S here. So this is a backward slip. Okay, it's a very important formula, friends. We will see one more question from this concept here. Next one. For a constant torque load, the voltage of the squirrel cage induction motor is reduced by 1 by 2 times. The current modified by a factor of. For a constant load, constant torque load, power is variable. So power is nothing but V into I here. So when the voltage is reduced by a factor of 1 by root 2 times, the current has to increase it by root 2 times, so that they also maintain constant power. So answer will be root 2 here. Okay. Next one. A 8-pole single phase induction motor is running at 690 RPM. It's a slip with respect to the forward and backward phase respectively. So first here, assuming the synchronous speed is approximately nearest to integer value, that is a 700 assume. Okay. So slip is equal to Ns minus Nr by Ns. So Ns value is how much? 700 minus Nr value is 690 divided by 700. Okay. So simply how much you get? 10 divided by 700, 1 by 70. Okay. So this will be the value of S value. Now which is equal to 0.08 I can say. Okay. The backward slip, you can say forward slip, backward slip is nothing but 2 minus S, that is 2 minus 0.08, which is nothing but 1.92 here. So answer will be 0.08 and 1.92. So 1 will be the right option for this question. Next one. The equivalent circuit of a double case induction motor, the 2 rotor cases can be considered as. For your convenience I have taken the diagram here. Okay, so here we have upper case and here we have lower case. Upper case will have high resistance, low reactance. Lower case will have low value of R and high value of X. So remember these points. This is very also important here. Now when you come to the equivalent circuit here, these 2 equivalent values are connected in parallel here. So the answer will be the equivalent circuit of a double case induction motor. The rotor will be considered is in to be in parallel. So these two are in connected in parallel here. So likewise also they will ask questions here. Okay, sorry. So next question is from microprocessors. How many number of input output ports are available in the 8051 microcontroller? Okay, so I have taken the diagram here, architecture diagram here. So as you see here, there are 4 input output ports, P0, P1, P2, P3. So the option is a 4 is a right option. How many external interrupts are there? INT01 and INT1. INT0 and INT1, the two are the interrupts here. Okay, counter inputs are T1, T0 here. Okay, next one. What is the output for the circuit given in figure assuming ideal diodes here? Okay, so here we have minus sign, here V0. Okay, so diode, for diode conduction should be diode, the anode to cathode should be positive value. So this condition satisfies means that diode is going to be conduct. For example, assuming initial case ground means 0 volts, assuming 0 volts here, first case. When 0 volts here also 0 volts, here also 0 volts, means both the sides are 0 volts. Here we have A and here you have K. So VAK should be positive value, or okay, ideal diode means positive value. See here same 0 volts is there, means anode to cathode. So VA minus VK, VA value is 0, minus of minus 5 is nothing but 5 volts. That means this diode is going to be conduct. And what about the voltage? When it's a conduction, output voltage will be minus 5 volts here. So answer will be 5 volts here. Okay. Next, the primary function of a filter is, so to explain that question here I have taken a full wave rectifier circuit here. Okay, and here we have a connected capacitor here. So capacitor is nothing but it acts as a filter here. Okay, now what will the options? Observe here, without filter, so full wave output waveform with a no filter here. No filter means you can see here the output will be a sinusoidal wave, half wave like this. Okay, here we have lot of ripples are there. When we are connecting a filter here, what will happen here is the voltage is going to be like this. So what it is going to do is it is going to remove the ripples here. So remove the ripples and make the output voltage constant value. Okay, so what it is going to do is it remove the ripples from the rectified output. Okay, it's going to be make this DC value. The capacitor is a very high value, then we will have a constant DC voltage. Okay, suppose if we use an inductor there, if we use the inductor value, then we have a constant current. Okay, for making the capacitor voltage constant, we will use a for making the output voltage constant, we use capacitor. For making output current constant, we use a inductor here. Okay. Next one, if one of the diode in a full wave bridge rectifier opens, the output will be. So to explain this question here, I have taken the full wave rectifier here, and here the positive half cycle, and here we have negative half cycle in a blue color. Okay, as you can observe here. Now for the positive half cycle, the output will be blue color. Here is a red color here. For positive half cycle, it's a red color. Positive half cycle. For negative half cycle, it's a blue color. Okay, so when any one diode gets open circuited, then we have a, for entire full cycle, and for entire full cycle we have only half output here. See here, either positive or either negative diodes here. So that means the full wave rectifier, if the diodes gets damages here, diodes get damaged, okay, then it's going to be become a half wave rectifier. So answer will be, it becomes a half wave rectifier. Okay, so we'll move to the next question here. The voltage amplifier, the load resistance should be, for a voltage amplifier, the load resistance should be, the options are as large as possible, as small as possible, and equal to output impedance and equal to input impedance here. Okay, so for a voltage amplifier, the load resistance should be as high as possible. So answer will be A here. Okay, next one. Generally, the gain of a transistor amplifier falls at high frequencies due to. So, at higher frequencies, what will happen? Xc is proportional to 1 by f. The frequency value is very high. The Xc value is very short, less value. When the Xc value is very low value, what about the voltage? Say simple resistance is very low value. What about the voltage? Voltage reduces here. So, voltage reduces means gain reduces here. Okay. So, it is because of the internal capacitance of the devices. So, internal capacitance is going to be internal capacitive reactance is very low here. And next question here, minimize the following Boolean function here. Okay, so I have taken a Boolean K map here. So I will take the K map. So I will take the K map here to simplify this function. Let me take a variable A here, and here BC, B bar, C bar, B bar C, and BC, and BC bar, and here also A bar and A here. So here 0, 1, 3, 2, 4, 5, 7, 6 here. Okay. So summation of M maximum value is 0, 1, 6, 7. So 0, 1, 6, 7 here, and don't care conditions are 3 and 5. So don't care about 3 and 5. So see here, in this particular row we have common A bar here, and what about the uppercase here? So in this case B bar is there. Okay, A bar, B bar plus, and here we have common is A, and in this 7th and 6th we have common as a B. So B. So answer will be A bar, B bar plus AB. So answer will be the first option here. So that's it for this session, friends. We will continue in the continue these questions in the next upcoming videos. Thank you. If you like this video, please share with your friends, and if you really like the video, please give a comment here. Okay. Thank you. Have a nice day.